Okay, just to remind you before I make a start, and perhaps most of you are familiar with semester one, where you undertook some clicker sessions. For those who didn't do PTA in semester one, the clicker sessions are a way of reaffirming or reinforcing your knowledge. We've prepared some key questions. For you to engage in this process, you need to have a clicker. You can choose either of the two options at the front. One's just an older version of the same thing. As I said to you earlier, if you can just return your clicker to the correct box, it makes it easier to sort out. How they run is that I've prepared 10 questions based on both the online material that I expect you to have learned, as well as some of the content we've done in our lectures thus far. In the following slides, I will give you the slide from the lectures or the online content that you needed to know in order to answer the question. So what I've tried to do is link the questions to content in the lectures. So you can see that if you learn the lecture content, you can answer the questions that I will ask. Okay, some of the questions build on each other, so there's presumed learned knowledge as we go through. I think you'll get the idea of how we do it. As I said, 10 questions. If we finished early, that's fine. If people have other questions, don't hesitate to ask. It's meant to be interactive for the people who turn up, with due apologies of those who haven't turned up. I will not feel that I need to stand behind the lectern and speak into the microphone. It is meant to be engaging with the audience who are here. So apologies in advance if I move away from the lectern, but these things don't work as well if I'm stuck behind here. Okay. I'll also be using the laser pointer. It's much easier to do so. So again, I'll put the questions and the answers up on your LMS probably tomorrow. There was no point obviously putting the questions and answers up before, or the questions up before, because I want to see what your knowledge is now. I'm sure you do too, rather than how well you can answer them from the textbook. Enough of the prelude. Question 1, fairly straightforward, comes from, I believe, the online material. So this will give you a thought about how you've accessed the online material. I've spoken a lot, you've read it. I will start the process now of counting down, 28 seconds to go. If you haven't used it, you just put A, B, C, D and E. You can change as many times as you want until the time runs out. At that point, you are locked into your answer. Okay, we've got 54 responses, which kind of seems like most of you had a go at this, which is fairly straightforward. The other thing is, if you don't know the answer, have a guess. There's obviously no assessment associated with that. It gives you an idea of how confident you are when you guess as well. This was based on something I spoke about ad nauseum, and that is one of the major features of the anatomical structures of the respiratory system, as well as getting air to and from the alveoli, which is in fact obviously its major important function. Don't underestimate the importance of making sure that the air that gets to your alveoli is as devoid of viruses, bacteria, or particulate matter, dust or whatever, as possible. Because if any of those get into the very delicate structures of the alveoli, it will cause inflammation, potentially infection, and as we learnt from Fick equation yesterday, that will compromise your ability to gas exchange. Protection, really important. So this question says, which of the following 5 structures is not directly involved in the protection of the respiratory membranes, the alveoli? Let's see what you thought the answers would be. Why isn't this? Because I pressed delete. Okay, most of you thought the answer was C, but it was less than half of you. Some of you thought the macrophages in the alveoli, basically 1 out of 4 of you thought that, and about 1 in 5 thought the trachea didn't play a role. The good thing about the anonymity of this is that I can say things that are not, don't take them personally. I'm not meaning to be rude or direct, but clearly, if you said D and E, D or E, I would suggest you might need to relook at the online material, or maybe you haven't had a chance to look at it. I can't imagine you've looked at the online material and still thought D and E, but that's okay. As I said, don't take any of this personally. I'm happy enough because, in fact, C is the correct answer. So let's go through it. 1 out of 4 of you said E. So why might have you said E? Well, I've no idea. But in fact, maybe because you didn't understand what macrophages were. A macrophage is a structure which removes foreign material. It engulfs it, it destroys it, and it allows you to remove it from the body. That's the whole point of macrophages throughout our body. The alveoli have 3 types of cells. You might recall from the online material. 1, which is the structure of the alveoli. 1, which are the surfactant secreting cells. And the 3rd type of cell are macrophages, which roam the alveoli, removing any particles that have escaped any of the other protective mechanisms. So macrophage is incredibly important. They're the last line of defence. So generally, if something's got through all the other lines of defence, the macrophages should, if you are healthy, remove particulate matter so you don't get infections. So review online. For those of you who said trachea, why might you have said trachea? 1 in 5 did. Well, I guess you might have thought that trachea is, the windpipe. It's a big hollow tube surrounded by cartilage. Its main job is to get air to and from the lungs. That is its main job, I guess. but a very important role. Again, maybe you perhaps didn't have a look at the online material because we did spend some time online talking about it. But the trachea is lined by what? Do you remember? Anyone want to help me out? Yeah. The trachea is in fact probably the most important structure to remove particulate matter, because as the internal lining of the trachea contains goblet cells. And what do goblet cells produce anywhere in the body? Mucus. So we've got a layer of mucus in our trachea. We've also got these specialised epithelial cells. Epithelial cells are surface cells, and they've got these cilia, hair-like structures or finger-like structures, and they're in constant motion. So we now build up a picture. You breathe in particulate matter and it gets to the trachea, which is a midline defence, the middle order of defence. The dust, viruses, bacteria will have a very good chance of sticking to the mucus. And obviously if they stick to the mucus, they can't go to the alveoli. You don't want it to build up, so these finger-like projections of the epithelial cells push the mucus constantly, 24 hours a day, pushing the mucus upwards. It gets to the pharynx, which is where you've got the joining of the esophagus, and you swallow it. And your digestive enzymes and the very acidic pH of your stomach will destroy any, well, hopefully destroy any particulate matter. So trachea is incredibly important in protecting the delicate alveoli. I would have thought some of you might have said A and B because they're not as important as D and E, in fact. But I guess A is fairly relevant because I guess in the live lectures I did speak about this, so maybe you remember it from lecture 1. The nasal cavity, look, it has some role of protecting you. Mainly the role of the nasal cavity is to in fact create a turbulent flow, warm the air, humidify the air. Now that's not protecting the alveoli, that's just making it easier for you to breathe. It's not protection. But what does the nasal cavity have that does protect you from the particulate matter? Nothing more than nasal hairs and some mucus. But it's not very effective. It really will only filter out large particles, large dust particles. That's all it's doing. So, first line of defence, nasal cavity, but certainly not the most important. But luckily, virtually none of you said it was. The pharynx, we again spoke about this in the live lectures, which is perhaps why some of you got it, even though it's not obvious. Pharynx has these pharyngeal tonsils, which again has some sticky substance. The dust will stick to it. Remember, the air has to do a right-angle turn. Particles will travel are heavier than air molecules, oxygen and nitrogen and carbon dioxide. So if you breathe it in very quickly, they'll hit the back of the pharynx, stick to the particulate matter, and be broken down by the pharyngeal tonsils immune system. So not many of you said that. Most of you said C. Let's stick to the positives. Most of you got it right. Trachea, the larynx, has no real role in protecting the respiratory system. What information did you need? Well, you needed to look at this diagram in the online presentation, and I spoke for about 10 minutes to this diagram about what these structures do. So go back online, have a look at that, the talk around this diagram, and you'll get all the information you need to answer question 1. Everyone happy with that? Question 2. Go to it. Polling open. I'll press the minute to go when probably half of you have answered the question. That'll be my reminder. Thirty-second countdown. Okay, finalise your answers or guess. Okay, polling closed. About 56, not about, 56 of you had a go at that, a little less. That often gives me an idea that it's level of difficulty. Let's see. And often with the level of difficulty comes a more even spread of answers. So let's see if that prediction holds true. This one's obviously about surfactant. We did this in the live lecture where we spoke about the function of surfactant. And we spoke about the surfactant having two important functions. Does anyone want to hazard a guess what they are? Yeah. The function of the surfactant is to reduce the surface tension, which is a fancy way and a very correct way of saying reduce the cohesive forces between aligned water molecules. So water molecules stick very closely together or very cohesive, so cohesive that it's nearly impossible for them to separate. The whole point is we've got an alveoli that's lined with water molecules. If you want to breathe in, you need to enlarge the alveoli, and if the water molecules' cohesive forces are too strong, you can't do it. So we need something to weaken those cohesive forces, and that's where we produce surfactant. It's kind of like a detergent. The other thing that surfactant does, so you don't want too much surfactant, you want just enough so that it takes a little bit of work to breathe, but not so much that you can't do it. The other thing about surfactant is that we proportionally produce surfactant according to the size of the alveolus. So big alveoli produce different amounts of surfactant to smaller ones. And this means that irrespective of the different size of the alveolus, the tension in them will be the same. Because obviously if the tension, or the pressure in them is the same. If the pressure in different sized alveoli are different, air always moves up and down pressure gradients. So in order for all the alveoli to have air in them, they have to have their pressures equal. Okay, so that's what we're looking at. Now, with that knowledge, I've kind of answered the question. So, look, I must admit I don't like double negative questions because I always look at that and think, oh, God, I can't understand this, than two negatives. I would never ask that in an exam question because I think it's asking you to comprehend things under pressure, which is not really fair. I should be testing your knowledge, not how well you can work through a riddle-type question. But for this, it's okay. It's not worth anything. So which one would not be a consequence? So 4 of them would be a consequence. Let's see what you said. Okay, I thought there might be a spread. There's not. Nearly all of you said B. 2/3 of you said B. I'm pretty happy with that because, in fact, B is the correct answer. The people who got it wrong, the 1 out of 3 of you who got it wrong, you kind of were spread across the board. I'm not getting a message that there's something key that I might have said that confused you or whatever. I kind of think you either knew it and answered B or you kind of were spreading no matter what. So not really a need to talk about a particular answer per se. I mean, all the other 4 smaller alveoli would collapse. Yes, they would. That's why we had surfactant, as I said. C, it'd be more difficult to enlarge it, and therefore inspiration is enlarging it, and breathing would be more difficult. So that C, D, and E are all related to each other. They all are saying the same thing. Okay, so, and they couldn't all be right, so they have to be all wrong. And you know they're all wrong anyway. Everyone happy enough with that one? Let's move on. The information you needed, you might recall that diagram and the words that I had in my slide in the first lecture. That's what you needed to recall to be able to answer the previous question. So if you didn't know the answer, review that slide and that will teach you what you need to know. Question 3, Fick's equation, my favourite equation. I need to get out more. counting down 30 seconds. Okay, last minute guessing, 54, fairly consistent. My reckoning is that this is relatively straightforward. Let's see if you thought that, which is after all the most relevant. Okay, not as straightforward as I thought. Fick equation we did yesterday. Yep. And if somebody said to you, give me one word that you associate with Fick equation. So you're doing those word association games. If somebody said Fick equation, it'd be a very boring word association game if they did. But anyway, let's say you're at a very boring dinner party and somebody says word association game, Fick equation. What word would you think of? One word. You'd go elsewhere, fair enough. It starts with D. Diffusion. Fick equation's all about diffusion. Diffusion of gases. So which one of those, that's all the knowledge you needed really to have. If you had that bit of knowledge, you could work out, okay, which of A, B, C, D and E is most relevant to diffusion. Not saying that the others are not relevant to respiratory function, but what's relevant to diffusion. And really there's only one of those that is most relevant to diffusion. And that is the one that more than half of you, but only just half of you said, which is E, which is the correct answer. A and C was kind of ridiculous, and most of you thought that, but D, a third of you said that. So let's have a look at why you might have said that. Look, all of these have a function. So really quickly, what is the function of the elastic fibres surrounding the alveoli? Why do we have elastic fibres surrounding the alveoli? What is their function? Yeah, to allow alveolar recoil, to make the alveoli get smaller. Now, when do you need your alveoli to get smaller? When you are wanting to exhale, breathe out. So, really important. But have they got anything to do with diffusion? No. Gas exchange? No. So, C certainly... start again. D certainly can't be the correct answer. So maybe you didn't quite understand what Fick equation was, and if you didn't, it's understandable. You'd think that D might be kind of an accurate thing to say, but it's not the right answer. Certainly, Fick equation relies on the others. B maybe, wide diameter of the trachea. What's the whole point of wide diameter of the trachea? What will that help you do? Perfect, well done. To help you get airflow. Because remember, flow, be it airflow or blood flow, is related to pressure and resistance. And trachea's diameter is all about resistance. So wide diameter means low resistance, which means big flow. Really important, anything to do with diffusion directly? No, indirectly, yeah, if you can't get air in, you won't diffuse, but directly, the question says direct influence? No, nothing to do with it. A and C, obviously only one of you said that, so I don't really care. So it's E. I care about you, I'm sure I do, but I don't care about wasting your time if only one of you got it wrong. Fick equation, what's it all? What are the key elements of Fick equation? I mean, the solubility of the gas, but that's kind of, we can't control that. Can't control that at all, sorry. Surface area. So really, Fick equation's about solubility of the gas, we can't control that. Pressure gradients, which we can control. Surface area, which is related to the large number of alveoli. And thickness inversely proportional to the thickness of the membrane, which we can't directly control either. So, alveoli, it's all about that. Nobody unhappy, upset? Next question. This is obviously the information you needed from yesterday's lecture. Surface area, there you go, Fick equation. Next question. This relates to lecture 2, I think, mechanics of breathing. Thirty-second countdown. Okay, 57. We managed to coax one extra person to answer a question, which is terrific. Tell them I'm busy. This is fairly straightforward, I think, too. It's about the mechanics of breathing, and you just needed to apply some of your learning to this. It's not too difficult a concept, but you did have to have some working idea of what was going on. Let's see how people went. Yeah, and I'm not surprised. I'm happy, pleasantly unsurprised that most of you thought that A was the correct answer and most of you were right. So 4 out of 5 of you probably means we don't need to talk about it too much. A few of you said B, which I guess if you're going to get confused, B was the obvious confused process. There are 2 things you needed to deconstruct. Basically, in the stem of the question, you've got your muscles contracted and you needed to recognise diaphragm and intercostals are the relevant muscles. It kind of would have been stupid if I said, you know, your biceps and triceps are contracted, you know, that's kind of ridiculous. So you would have worked out that these are the muscles of breathing. So that's the first thing, they're contracted, key word. And the second thing, no air moving, second key words. So let's take the no air, because most of you got that right. So if there was no air moving through the airways, you could immediately rule out C and D, because obviously inspiration and expiration involves continuous movement of air. Certainly in the middle anyway. Maybe right at the end it might stop, towards the end, but certainly in the middle, that's when you're going to get quite a lot of air movement. You could have been at the end of inspiration or expiration, or indeed dead, and no air would be relevant to that. So in order to work out what of A, B and E is correct, muscles contracted. So when are your muscles going to be contracted? When you're dead, no, unless you're in rigor mortis. But I didn't say that. I didn't say dead and in rigor mortis, which would make it correct. So we're kind of looking at A and B. At the end of inspiration or the end of... So maybe the one person who said dead, you probably thought rigor mortis, so all power to you. Well done. Always look at the positives in people, always. A and B, inspiration, expiration. Well, kind of how would you make your decision on that? Most of you did decide correctly. You contract your muscles during inspiration. Inspiration is active work, expiration passive. No muscles contract during quiet expiration. If you said B, you might have said, what about forced expiration? Well, you'll be right, but remember, we're always looking for the most correct. And A is always correct. B is only correct in certain circumstances. So A is clearly the best answer. Most of you got that right, the information you needed. Clearly that diagram I showed in the lectures, looking at what happens to pressures and movement of air. So no air movements happening here, muscles are contracted here. So you needed to be familiar with that mechanics. Next question, we've suddenly got an answer now. Don't know where that came from, but it is not irrelevant. Please do answer now. Building on the last question, by the way, which most of you got right, so that's a good thing. 30-second countdown. Okay, bit of a flurry at the end, didn't quite get the maximum number, and that's perhaps because I rushed you a little bit, but this question again is relating the mechanics of breathing and it's probably making it a little more complex. Having said that, it's not a difficult question, it just has an additional level of complexity. Because I'm asking you to make a decision about, to understand what's happening to intrapleural pressure, alveolar pressure differentials, that is how it's different from the atmosphere, and surface tension. Now the good thing about this question, you didn't need to know what's happening to each of those three to answer the question. You needed to know at least one of them and preferentially two. So you still could have answered it if you had no idea about one of them. So let's see how people went, and again, probably related to the level of complexity of the question. Majority of people said A, but it wasn't the majority of people in the audience. So less than half of you said A. About a quarter of you said B or C, and D and E was negligible. Let's see what the answer is. The majority wins again, but it still is fewer than half of you. So well done if you got that correct. Let's deconstruct it. Look, as I said, you could look at any of those. So let's look at the, maybe the middle one first, just because it suits me to talk in this order. Alveolar pressure is different from the atmosphere. So if alveolar pressure is different from the atmosphere, what must be happening? Air must be flowing. Let's put a full stop after flowing. We can't say in or out. We just say air is flowing. Because as long as the airways are open and there's a pressure difference, air will be flowing. Now, we don't know if it's in or out because I haven't said how it's different. Just said it's different. So the answers that don't say air is flowing must be wrong, simply by looking at that. So we can draw a line through C, a person must be about to breathe in. Because if you are about to breathe in, there's no air movement and there could be no pressure differential. If I said a person is breathing in, but somebody's blocking their mouth and nose, you might be right, but I certainly didn't say that. So if there's no air, if you're about to do something, it's not yet happening, so there's no pressure difference. So C and D can't be right. If we then look at surface tension, which is probably the second easiest thing to work out, surface tension is increasing. So when might surface tension increase? And again, I did this primarily online. When the alveoli are getting bigger, because the water molecules are being stretched apart. So what do they want to do more than before? Come back together again. It's kind of like stretching an elastic band. I mean, it's not the best analogy, but it kind of works. So the bigger the alveolus is, the more stretched the water molecules are, and the bigger the surface tension is to try and shrink them back together again. So you have got higher surface tension when the alveolus is bigger. So the alveolar surface tension is increasing. You have said to me the alveoli are getting bigger. And does that happen when you're breathing in or out? When do your alveoli get bigger? During inspiration or expiration? Inspiration. So that tells us it can't be breathing out or forcing breathing out. So it has to be A. Now, you could have even answered that without looking at intrapleural pressure, but if you wanted to incorporate that as well, and you could have, intrapleural pressure does become more negative as you breathe in, because obviously if your thoracic cage or cavity is getting bigger, the intrapleural pressure becomes more and more subatmospheric. But I kind of didn't think it was just right time to ask you to work that out just yet. The information you needed is all accessible in this diagram that I showed in the lecture. It shows you what's happening to alveolar pressure. And before you breathe in or after you breathe in, before you breathe out, after you breathe out, it is 0. That is the same as the atmosphere. It certainly does decrease, and intrapleural pressure certainly does decrease during inspiration. So that gave you the information that you needed. Didn't talk about surface tension, but it would have enabled you to answer that question. Time for a couple more questions. I've said I've taken this from Widmer, but I've certainly taken it from your lecture notes, which is more relevant to you. So this diagram comes from the lecture notes yesterday. Let's see if you understood what we were talking about then. Thirty seconds. Okay, polling closed. 53 responses. Now, if we get the majority going in, I haven't left enough room for that to be displayed, but we still should get an idea of what's going on. We can work out, well done, we can work out that B must be 81%. So, very happy that B is 81% because that is the correct answer. So, most of you got the point of yesterday's diagram. So what was the diagram all about? Well, clearly it's all about dead space, but what is it telling us about dead space? Now, A and E, none of you said, so I don't know why I was fixated with dead people that day. I was obviously watching lots of episodes of Grimm or something the night before I prepared those questions. Bigger breath leading to a bigger dead space, well, everyone got that right, and they said it was wrong, which was good. The dead space can't change. That's you. You've got anatomical structures with a certain volume. That's not going to change dramatically. So B, C and D were the more likely choices, but again, D, 1 out of 8 of you said that, so not a real drama. Dead space always consists of atmospheric gas. Well, given that atmospheric gas is coloured in this diagram in orange, the left-hand side clearly says it doesn't. When you breathe out, you haven't got atmospheric gas in your airways, you've got alveolar gas. It's come from the alveoli. When you breathe in, after you breathe in, you've got atmospheric gas, so-called fresh air. After you breathe out, you've got alveolar gas, so-called stale air. So clearly, dependent upon what stage of the breathing cycle you are in, the contents of the dead space are different. So the point of this question was to remind you that the dead space, you can't think of the dead space as having atmospheric gas or alveolar gas. It can have either, depending upon what you have just done or in the process of doing. Okay, and that is what B is saying, so well done. 4 out of 5, don't need to spend much more time on that. The obvious thing you needed to look at was the one that I showed you, so we can move on from that. This might be the second last one, the last one, which is fine. We're right on time. 30 seconds. Okay, 53 responses, pretty good response rate. Let's see what people thought. I've got a feeling most people might get this right. No, I'm wrong. Spread. Okay, that surprises me. I guess it's a little bit tricky in that it's saying which of the following would lead to a bigger than normal expiratory breath, and that's obviously the key phrase. Well, certainly greater than normal and expiratory are the key words. So a bigger breath out. And all the options are increasing things. So maybe that's where people are getting a bit confused. All of them are increasing. So maybe we shall see what the right answer is first. And again, even though way, way less than half of you said E, in fact only slightly out of 1 out of 3, you were correct if you did say that, so well done. But we've had between 1 in 10 and 1 in 5 of people say other options. So we need to go through them all. So a greater than normal contraction of the diaphragm, would that lead to expiration being bigger? Obviously not, it's the wrong answer, so maybe my question should be, why won't that lead? What's the diaphragm involved in? Inspiration. Question 1 or 2 of this session told you the muscles of inspiration are the diaphragm and the intercostals. They've got nothing to do with expiration. Well, they relax. Sorry, I shouldn't say nothing to do. They are involved in expiration when they relax. Expiration is all about relaxation, quiet expiration. And even if you're saying, well, it's not quiet expiration, it's forced expiration. But again, to the diaphragm, can that, if you contract it harder, all that's going to happen is you're going to get a bigger breath in. Other muscles are involved in expiration. Can you remember what muscles might have been involved in forced expiration? Yeah, particularly the abdominal muscles. They contract the contents of the gut, shove the gut into the diaphragm, making the diaphragm more bell-shaped, which makes the contents of the thorax even less than before. So, greater contraction of the diaphragm. If it said normal, a bigger than normal inspiratory breath, tick, A's right, but it's expiratory, it is wrong. Does the 1 out of 4 of you said that understand why you were wrong with that? Yep. B, increased frequency of action potentials. Now, we haven't really addressed this in the lecture, but I was relying on people knowing from year 1 or semester 1 that if, and I think I did say it, if you want to contract a muscle harder, what do? In fact, I'm sure I said it, increase the frequency of action potentials. So increasing the frequency of action potentials is going to make your intercostal muscles. You might say, how was I supposed to know that the intercostal nerves innervate the intercostal muscles? Well, I kind of think that wasn't too much to ask you, because both have the word intercostal. So the intercostal nerves, in case you couldn't work it out, innervate the intercostal muscles. So contracting the intercostal nerves more, studying. Increasing the frequency of action potentials will lead to a bigger contraction of the intercostal muscles, which will lead to a bigger inspiration. Again, it's all about inspiration, A and B. So maybe that's where those 2 out of 5 of you who said A or B were getting confused. That's inspiration, not expiration. Increased thoracic volume. Well, if you remember old, what's his name? Boyle's law. Increasing the volume of the thorax will increase the volume of the alveoli, because the thorax, the lungs change in shape the same as the thorax because of the intrapleural connection. So thorax gets bigger, so does alveolar get bigger. So C and D have to be the same, so you can't really say one of them's the answer and the other's not. But irrespective, if you increase the volume of the thorax and hence the alveoli, what did Boyle say happened if you increase the volume of the alveoli? You reduce the pressure, and what will air do? Down to a smaller pressure, it'll flow in. So this is all about inspiration. So A, B, C and D are all about bigger inspiration. Expiration, increasing the intra-alveolar pressure. Now, fairly straightforward. That's the pressure inside the alveoli. So if the pressure inside the alveoli is bigger than normal, what will happen? More air will be pushed out than normal. What do we call pushing air out? Expiration. So that's why E is the answer. Happy enough with that? Nobody's still confused? Yep.
You know, with forced expiration, you've got the internal intercostal muscles that aid that as well, so B could be right.
Not so much B could be right, but you could have been misled into thinking that B is right. It's not the same intercostal muscles. I differentiated between external and internal intercostal muscles. So I guess I haven't specifically said that the intercostal nerves innervate the external intercostal muscles, but they do. Different nerves innervate the internal intercostals. I guess you might be saying, how do I know that? I guess what I'm relying on you to know is that the intercostal nerves innervate the principal intercostal muscles, which are the external ones which are involved in inspiration. If you said, well, that's kind of a bit unfair because you're assuming I knew something, I guess I was assuming that E is clearly right, and if you had to make a choice between something that is clearly right and something which you had to suppose I meant something and meant something else, always go for the one that's clearly right. Okay? So it's a really good point. Thanks for raising it. It does make you think that, in fact, if you don't ever second guess yourself, if you're thinking, oh, this might be right if you meant that and that and that, well, sure, do that if you think all the others are wrong. But if you think E is right and you're second guessing yourself against B, E will be right. So that's good example. Thank you. I think I got out of that pretty well. I'm just wondering if that was the last question or this one. Oh, and obviously the overhead you needed to know, the slide in the lectures you needed to know to work that out, is that same one again that I said in the lectures was pretty important to understand what was going on during inspiration and expiration with all the pressures. We've got 5 minutes. I'm just going to see. Okay, let's look at this one. This is the second last one. It doesn't matter. We can carry the one over to clicker session number 2, which you've got in a couple of weeks' time. But let's finish off with this one. It's relatively straightforward, relying on information about your volumes and capacities that we spoke about at the beginning of yesterday's lecture.